Close your eyes and imagine standing at the edge of time itself. Not tomorrow, not next year, not even 1,000 years from now, but 1 billion years into the future. A span so vast it challenges comprehension. Roughly 70 million human lifetimes stacked end to end. In that distant epoch, the Earth you know will have transformed beyond recognition. The continents will have drifted into new configurations. The climate will have shifted in ways both subtle and profound. Life, if it persists, will have adapted to conditions we can barely imagine. Tonight, we embark on a journey through deep time, guided by geology, astronomy, solar physics, and evolutionary biology. This is not speculation for entertainment, but extrapolation from what we understand about planetary processes. We will move slowly through the mechanisms that shape our world across incomprehensible timescales. The slow burn of our aging sun, the patient drift of tectonic plates, the relentless evolution of the atmosphere. There will be no catastrophic drama here, only the quiet, inexorable forces that have shaped Earth for 4.5 billion years and will continue shaping it for billions more. Let us begin this meditation on geological time. To understand Earth 1 billion years hence, we must first grasp the forces already in motion. Our planet is not static. It never has been. Beneath the thin crust we inhabit, the mantle churns in vast convection currents, driven by heat from the core and the decay of radioactive elements. This movement, imperceptibly slow by human standards, drives the dance of continents across the globe. Tectonic plates drift at rates measured in centimeters per year, roughly the speed your fingernails grow. Over millions of years, these incremental movements accumulate into dramatic reshaping. Mountains rise and erode. Ocean basins open and close. Continents collide and fragment. This process, called plate tectonics, has operated throughout most of Earth's history and will continue operating far into the future. But plate tectonics is not the only force at work. Our sun is also changing, growing gradually brighter as its core fuses hydrogen into helium. This brightening, about 10% per billion years, will have profound consequences for Earth's climate and habitability. Together, these forces, internal geological processes and external solar evolution, will sculpt the Earth of 1 billion years from now. Let us begin with the sun, for it is the engine that powers nearly everything on Earth's surface. Our star is approximately 4.6 billion years old, halfway through its main sequence lifetime. It formed from a collapsing cloud of gas and dust, and for billions of years has maintained a delicate balance. Gravity pulling inward, pressure from nuclear fusion pushing outward. But this balance is not perfectly static. As the sun fuses hydrogen into helium in its core, the composition changes. Helium is denser than hydrogen, so the core slowly contracts under its own weight. This contraction raises the temperature, which increases the fusion rate, which produces more energy. The result is a gradual brightening of the sun over geological time. When life first emerged on Earth roughly 3.8 billion years ago, the sun was about 30% dimmer than today. Over the next billion years, it will brighten by approximately another 10%. This may sound modest, but the effects on Earth will be anything but subtle. That additional energy will drive changes in temperature, weather patterns, and the fundamental chemistry of the atmosphere. Understanding solar evolution is essential to understanding Earth's distant future. 10% more solar energy sounds almost negligible, a small adjustment surely manageable. But climate is a system of delicate balances, and even small forcings can trigger large responses. Consider that the difference between our current climate and the last ice age, when glaciers covered much of North America and Europe, corresponds to a global temperature change of only about 5 degrees Celsius. The increase in solar output over the next billion years will inject vastly more energy into Earth's climate system than that. This energy will manifest in multiple ways. Surface temperatures will rise. Evaporation rates will increase, putting more water vapor into the atmosphere. Water vapor is itself a greenhouse gas, so this creates a feedback loop. More warmth causes more evaporation, which causes more warming. The oceans, which currently absorb enormous amounts of heat and help moderate climate, will gradually warm. As they warm, they will hold less dissolved carbon dioxide. This CO2 will escape into the atmosphere, where it will further enhance warming through the greenhouse effect. These feedback mechanisms can amplify relatively small initial changes into dramatic transformations. The increasing temperature will accelerate a process called silicate weathering. This is one of Earth's most important climate regulation mechanisms, and it operates on geological timescales. When rain falls, it absorbs carbon dioxide from the atmosphere, forming weak carbonic acid. This slightly acidic water reacts with silicate rocks exposed at Earth's surface, breaking them down chemically. The products of this weathering eventually wash into the oceans, where marine organisms use them to build shells and skeletons from calcium carbonate. When these organisms die, their remains settle to the ocean floor, eventually forming limestone. This process, weathering of silicates, transport to oceans, incorporation into carbonate rocks, is a vast pump that removes CO2 from the atmosphere and locks it away in solid rock. The rate of this weathering depends on temperature. Warmer conditions mean more rain and faster chemical reactions, which accelerates CO2 removal. This creates a negative feedback that has helped stabilize Earth's climate over billions of years. But there are limits to how much this mechanism can compensate for a brightening sun. As temperatures rise and weathering accelerates, atmospheric CO2 levels will drop. This might seem beneficial, a natural thermostat cooling the planet as the sun brightens. And for hundreds of millions of years it will work to a point. But CO2 is not just a greenhouse gas. It is also essential for photosynthesis, the process by which plants and other organisms convert sunlight into chemical energy. Plants take in CO2 through pores in their leaves called stomata. They use the carbon to build sugars and other organic molecules, releasing oxygen as a byproduct. Most plants today use a photosynthetic pathway called C3, which requires CO2 concentrations of at least 150 parts per million to function. Below that threshold, C3 photosynthesis becomes inefficient and eventually impossible. As weathering draws down atmospheric CO2, plant life will face increasing stress. Some plants use a more efficient pathway called C4 photosynthesis, which can function at lower CO2 levels. These plants will have an advantage. But eventually, as CO2 continues to decline, even C4 photosynthesis will fail. This creates a crisis point in Earth's biological history. The timeline for this CO2-driven crisis is uncertain and depends on complex interactions between geology, climate, and biology. Different models produce different estimates, but many suggest that atmospheric CO2 could drop below critical levels for plant life somewhere between 500 million and 1 billion years from now. Let us consider the more conservative scenario where plant life persists barely at the 1 billion year mark. By this time, photosynthesis will be under severe stress. C3 plants, which include most trees, will have largely disappeared hundreds of millions of years earlier. Forests as we know them will be distant memories, preserved only in the fossil record. C4 plants, which today include many grasses and some agriculturally important crops like corn and sugarcane, will dominate the remaining vegetation. These plants will be concentrated in regions where conditions remain marginally favorable, perhaps high latitudes, high altitudes, or areas with seasonal moisture. The tropics, now lush, will have become largely barren. The Great Amazon Basin, the Congo, Southeast Asia, all transformed into hot, dry wastelands where photosynthesis cannot keep pace with the demands of survival. The decline of plant life will cascade through ecosystems. Animals depend on plants directly or indirectly for food. As plant productivity drops, so too will animal populations. Herbivores will face shrinking food supplies and expanding deserts. Carnivores will follow their prey into decline. Biodiversity will contract, perhaps sharply. Evolution will favor organisms that can survive with minimal resources, extreme metabolic efficiency, long dormant periods, and opportunistic exploitation of whatever brief abundances occur. Some scientists speculate that life might retreat to refugia, small pockets where local conditions remain tolerable, perhaps deep caves where stable temperatures and moisture persist, perhaps polar regions where the brightening sun has not yet rendered conditions lethal, perhaps the deep ocean, where sunlight never penetrates and life depends not on photosynthesis, but on chemical energy from hydrothermal vents. In this scenario, Earth 1 billion years from now would host a diminished biosphere, a shadow of its current richness, but not yet entirely lifeless. Life, tenacious and adaptive, would cling on in the margins. While biology struggles with heat and CO2 depletion, the continents continue their ancient migration. Plate tectonics operates indifferently to the biosphere, driven by heat deep within the planet. Over the next billion years, the arrangement of continents will change dramatically. Currently, we live in an era of dispersed continents following the breakup of Pangaea, the supercontinent that existed around 300 million years ago. But supercontinents form cyclically. Continental drift follows a pattern called the supercontinent cycle, where continents periodically assemble into a single landmass, persist for perhaps 100 million years, then fragment and disperse again before eventually reassembling. The cycle takes roughly 400 to 600 million years. Given that Pangaea broke apart about 200 million years ago, we are currently in the dispersal phase. Over the next several hundred million years, the continents will begin converging again, driven by the motion of tectonic plates. 1 billion years from now, a new supercontinent may have formed, or may be in the process of forming. Geologists have proposed several scenarios for the next supercontinent, each named with playful grandeur. Pangaea Proxima is one model, in which the Atlantic Ocean closes as the Americas drift back toward Europe and Africa. The Mediterranean disappears, crushed between Africa and Eurasia. Antarctica migrates north, eventually colliding with other landmasses. Another model, called Nova Pangaea, envisions the Americas continuing westward to collide with Asia, closing the Pacific. A third scenario, Orica, combines elements of both. The Atlantic closes, but so does most of the Pacific, with continents assembling along the equator. Each model is speculative, extrapolated from current plate motions and assumptions about future mantle dynamics. Predicting continental positions 1 billion years hence is extraordinarily difficult because small uncertainties in current velocities amplify over such vast timescales. But what we can say with confidence is this: the continents will not remain where they are. They will collide, creating new mountain ranges. They will rift, opening new ocean basins. The map of Earth will be unrecognizable. The formation of a supercontinent would have profound effects on climate and life, independent of the sun's brightening. Supercontinents create extreme continental climates. With most land concentrated in one enormous mass, coastal regions shrink and interior regions expand. The moderating influence of oceans diminishes. Continental interiors become subject to temperature extremes. Scorching summers, frigid winters, minimal rainfall. The vast interior of a supercontinent, thousands of kilometers from any coast, would be a harsh, arid environment. Meanwhile, the single enormous ocean surrounding the supercontinent, sometimes called Panthalassa in reference to the ocean that surrounded Pangaea, would experience its own dynamics. Ocean currents would reorganize around the new continental configuration. Heat distribution would change. Regional climates would shift. Some models suggest that supercontinent formation could trigger ice ages, as large landmasses at high latitudes promote ice sheet formation. Others suggest intensified monsoons, as the temperature difference between continent and ocean drives powerful seasonal wind patterns. The exact outcome depends on where the supercontinent forms and how it is oriented relative to Earth's rotational axis. Let us pause to consider the ocean itself, for it will undergo its own transformation. Today's oceans are teeming with life, from microscopic phytoplankton that produce much of Earth's oxygen to vast schools of fish, squid, whales, and countless other organisms. The oceans are also major carbon sinks, absorbing CO2 from the atmosphere and storing it in multiple forms, dissolved in seawater, incorporated into marine organisms, settling as carbonate sediments on the ocean floor. But as the sun brightens and surface temperatures rise, the oceans will warm. Warm water holds less dissolved gas than cold water. This is why carbonated beverages go flat when warm, the CO2 escapes. The same principle applies to the oceans. As they warm, dissolved CO2 will escape back into the atmosphere, amplifying greenhouse warming. Dissolved oxygen will also decrease. Many marine organisms are sensitive to temperature and oxygen levels. As both change, ecosystems will reorganize. Species adapted to cooler, oxygen-rich waters will retreat toward the poles or to deeper, cooler depths. Coral reefs, already under stress from current warming, will face increasingly hostile conditions. The warming oceans will affect currents, those vast rivers of water that circle the globe, redistributing heat from the equator toward the poles. The thermohaline circulation, driven by differences in temperature and salinity, plays a crucial role in moderating regional climates. Warm surface currents carry heat poleward. Cold, dense water sinks at high latitudes and flows back toward the equator at depth. This circulation is sometimes called the ocean conveyor belt. Changes in temperature, salinity, and ice cover can alter this circulation, with far-reaching consequences. In Earth's past, disruptions to ocean circulation have triggered rapid regional climate changes. 1 billion years from now, with a warmer planet and different continental configuration, ocean currents will have reorganized into new patterns. The details are impossible to predict with certainty, but we can be sure the circulation will differ substantially from today's. Some regions that currently receive warmth from ocean currents may become colder if those currents shift. Others may warm. The oceans, like the continents, will be transformed. Water itself may become scarce on land. As temperatures rise, evaporation accelerates. Water vapor enters the atmosphere but may not return to land as precipitation in useful amounts or locations. Atmospheric circulation patterns will shift in response to changing temperature gradients. Deserts will expand. River systems will dwindle or disappear entirely as their sources dry up. Lakes will evaporate. The water cycle, which currently sustains terrestrial ecosystems and replenishes aquifers, will reorganize. Some models suggest that in a much hotter world, water vapor could accumulate in the stratosphere, where solar ultraviolet radiation would break it apart into hydrogen and oxygen. The light hydrogen atoms could then escape to space. This process, called hydrodynamic escape, operates slowly but relentlessly. Over hundreds of millions of years, Earth could lose a significant fraction of its water inventory. Venus may have experienced this fate. Early in its history, Venus likely had liquid water, but runaway greenhouse warming vaporized the oceans, and solar radiation stripped the water vapor away. Earth 1 billion years from now may be on a similar trajectory. The loss of water would be catastrophic for life. All known organisms require liquid water. It is the solvent in which biochemical reactions occur, the medium that transports nutrients and removes wastes, the substance that maintains cellular structure. Without water, biochemistry as we know it cannot function. If Earth begins losing its oceans to space, the biosphere's days are numbered. But let us not rush toward that conclusion. The timeline for significant water loss is uncertain and depends on atmospheric dynamics we do not fully understand. It is possible, perhaps even likely, that much of Earth's water will remain, locked in oceans, polar ice, and subsurface reservoirs, even as surface conditions become inhospitable. The oceans are vast, containing about 1.3 billion cubic kilometers of water. Losing a significant fraction of that through hydrodynamic escape would take extraordinary time and specific atmospheric conditions. So for now, let us assume that 1 billion years hence, Earth still possesses oceans, though they may be warmer, more acidic, and less friendly to life than today's. We should also consider the atmosphere's composition beyond just CO2. Earth's atmosphere is roughly 78% nitrogen, 21% oxygen, and trace amounts of argon, water vapor, and other gases. Oxygen is particularly interesting because it is maintained at high levels by photosynthetic life. Before photosynthetic organisms evolved, Earth's atmosphere contained little free oxygen. Cyanobacteria and later plants produced oxygen as a waste product of photosynthesis. This oxygen accumulated in the atmosphere over billions of years, eventually reaching current levels. It enabled the evolution of complex, large organisms with high metabolic demands. But oxygen is reactive. It combines with rocks in weathering processes, it reacts with volcanic gases, it escapes to space slowly through various chemical pathways. Without continuous replenishment by photosynthesis, atmospheric oxygen would decline over millions of years. If plant life collapses due to CO2 depletion, oxygen production would cease. Animals, which require oxygen for respiration, would face a double crisis: disappearing food sources and declining oxygen. The transition might take millions of years, but the endpoint would be an atmosphere far poorer in oxygen than today's. Imagine, then, the atmosphere 1 billion years from now. CO2 depleted to trace levels by silicate weathering. Oxygen reduced, perhaps to a fraction of current levels, as photosynthesis falters and geological processes consume what remains. Water vapor variable, potentially high due to evaporation from a warmer surface, but also potentially depleted if significant water loss to space has occurred. Nitrogen would persist. It is relatively inert and not easily removed from the atmosphere. Argon, produced by radioactive decay of potassium in rocks, would actually increase slightly over time. Volcanic outgassing would continue to inject various gases into the atmosphere: sulfur compounds, carbon dioxide, trace metals. The atmosphere's density and pressure might remain similar to today's, but its composition would be inhospitable to most current forms of life. This is not a sudden catastrophe but a gradual transition, a slow suffocation stretched across hundreds of millions of years. And through it all, the sun continues brightening, pouring more energy into a planet increasingly unable to dissipate it. What would the surface look like under these conditions? Close your eyes and envision a landscape 1 billion years from now. The sky, perhaps a different hue than today's blue, more whitish or pale yellow due to different atmospheric scattering and composition. The sun larger in the sky, slightly, almost imperceptibly, but brighter, harsh, beating down on a surface where shade is precious and water scarce. Continents assembled or assembling into new configurations, vast mountain ranges marking where tectonic plates have collided, their peaks newly thrust upward by continental convergence. But these mountains are sterile. No forests cloak their slopes, no alpine meadows dot their valleys. Only bare rock, perhaps stained with mineral deposits where ancient water flows have long since dried up. Lower elevations present expansive deserts, endless plains of sand and gravel baked under the relentless sun. Winds, unimpeded by vegetation, sculpt the sand into dunes, ripples, ventifacts. Dust storms rage across these barren lands, lifting fine particles high into the atmosphere where they scatter light and color the sky. Yet perhaps there are exceptions. Perhaps there are oases where life persists. Consider a high plateau near one of the poles, where temperatures remain marginally cooler despite the increased solar output. Seasonal precipitation, driven by the interaction between polar air masses and warmer air from lower latitudes, delivers moisture several times a year. Here, perhaps, specialized plants cling to existence, low-growing, with extensive root systems to capture every drop of water, with highly efficient photosynthesis to make use of the trace CO2 available. Around these plants, a sparse ecosystem, arthropods, perhaps, adapted to desiccation and extreme temperatures. Small vertebrates sheltering in burrows during the day, emerging at night to feed. Microorganisms in the soil, processing organic matter in slow motion. This would not be Eden but a tenuous foothold for biology. Species counts would be low, populations small, genetic diversity diminished. Yet it would be life persisting against the odds. Alternatively, consider the deep ocean. Far below the surface, where sunlight never penetrates, ecosystems today rely not on photosynthesis but on chemical energy. Hydrothermal vents, where heated water laden with dissolved minerals erupts from the seafloor, support communities of bacteria that oxidize sulfur, iron, and other chemicals, converting chemical energy into biological energy. These bacteria form the base of a food web that includes tube worms, clams, shrimp, fish, and other organisms adapted to the extreme conditions. Such ecosystems are independent of surface conditions and photosynthesis. They would be buffered against the changes transforming the surface world. 1 billion years from now, as surface ecosystems collapse, deep-sea vent communities might continue largely unaffected. Plate tectonics would still generate new seafloor at mid-ocean ridges. Volcanoes would still heat water. Minerals would still dissolve. Life at the vents could persist as long as geological processes continue. In this scenario, Earth's biosphere would retreat to the deep ocean, a hidden refuge from an increasingly hostile surface. The Moon, our silent companion for billions of years, will also have changed, though subtly. The Moon is slowly drifting away from Earth due to tidal interactions. Currently, it recedes at about 3.8 centimeters per year. Over 1 billion years, that accumulates to 38,000 kilometers, roughly 10% of the current Earth-Moon distance. As the Moon recedes, its gravitational influence weakens. Tides will be less pronounced. The Moon's stabilizing effect on Earth's axial tilt will diminish slightly. Earth's axis is currently tilted about 23.5 degrees relative to its orbital plane around the Sun. This tilt causes our seasons. The Moon's gravity helps stabilize this tilt, preventing large chaotic variations that could lead to extreme climate swings. With the Moon farther away, Earth's tilt may vary more over geological time, though the effect over 1 billion years would be modest. The Moon itself will appear smaller in the sky, though still visible. Total solar eclipses, where the Moon perfectly covers the Sun's disk, will become rarer or impossible as the Moon appears smaller than the Sun. Let us not forget Earth's magnetic field, generated by convection of molten iron in the outer core. This magnetic field shields the surface from the solar wind, a stream of charged particles flowing outward from the Sun. Without this shield, the solar wind would strip away atmosphere over geological time and increase radiation exposure at the surface, potentially inhibiting life. Earth's magnetic field has existed for at least 3.5 billion years, but it is not constant. The field's strength varies, and its polarity reverses irregularly. North and south magnetic poles swap positions every few 100,000 years on average. 1 billion years from now, the field should still exist, powered by core convection. However, Earth's interior is cooling. The core is losing heat to the mantle slowly, and this cooling will eventually solidify the outer core, shutting down the magnetic field. This process takes billions of years. Earth has enough internal heat for several billion years more of magnetic field generation. So 1 billion years hence, the magnetic field likely remains, protecting what remains of the atmosphere and biosphere from solar wind erosion. Geological activity, too, will continue. Volcanic eruptions will punctuate the slow march of time, injecting gases and particulates into the atmosphere, building new crust, reshaping landscapes. Earthquakes will rattle along plate boundaries where continents collide or pull apart. Erosion will continue wearing down mountains, transporting sediment to ocean basins, creating new sedimentary rocks that will themselves be subducted, melted, and uplifted in the endless rock cycle. Geologically, Earth will remain active. Plate tectonics may persist for another billion years or more, driven by mantle convection. The planet's interior cools slowly enough that dynamic geological processes should continue. This is important because plate tectonics is not just about moving continents. It is also the mechanism that recycles material between the surface and interior, that drives mountain building and volcanic activity, that influences climate through CO2 regulation via volcanism and weathering. A geologically dead planet, like Mars, cannot regulate its climate or replenish its atmosphere. Earth, 1 billion years hence, will still be geologically alive, even if its biosphere is diminished. And what of human legacy? If we assume humanity survives the next billion years, a monumental assumption, we would evolve beyond recognition. 1 billion years is roughly 200 times longer than the entire history of the genus Homo. Evolution over such timescales could produce descendants unrecognizable as human. Alternatively, technological civilization might persist, our descendants wielding technology capable of mitigating or escaping Earth's decline. They might engineer the climate, sequestering water, shading the planet, sustaining ecosystems artificially. They might abandon Earth for other worlds, leaving behind ruins that geological processes would erase over millions of years. Or perhaps humanity will have vanished long before, a brief chapter in Earth's long story. Our cities crumbled to dust, our plastic and concrete broken down, our satellites fallen from orbit, our nuclear waste decayed, our impact on the planet fading like so many other species before us. The Earth of 1 billion years from now likely bears no trace of us. Fossils, perhaps, if conditions preserve them, but nothing recognizable as human civilization. Time erases all. Let us shift perspective and consider not just what Earth will be, but what the journey toward that state looks like. We tend to think in terms of endpoints, final configurations, ultimate outcomes. But deep time is not a leap to a conclusion. It is a continuous unfolding, countless generations of change accumulating incrementally. The transition from today's Earth to the Earth of 1 billion years hence occurs gradually, almost imperceptibly at any given moment, yet cumulatively transforming everything. At the halfway point, 500 million years from now, Earth would already be substantially different from today. The sun's brightness might have increased 5%. Atmospheric CO2 might have dropped below levels that support C3 photosynthesis, leading to mass extinction of many plant species. Continents would have drifted noticeably from current positions, perhaps beginning to assemble into a new supercontinent. The climate would be warmer, weather patterns shifted. Yet from there to 1 billion years, another 500 million years of change awaits, doubling the differences. The Earth of 1 billion years from now is as far from the Earth of 500 million years hence as that Earth is from today. This gradualism is important because it shapes how life might respond. Evolution operates through natural selection, adapting populations to changing conditions over generations. When environmental changes are slow, species can potentially track those changes, evolving new tolerances, behaviors, physiologies. When changes are rapid relative to generation time, extinction becomes more likely. Over hundreds of millions of years, the pace of solar brightening and geological change is slow enough that life, remarkably adaptable, might repeatedly reinvent itself, finding new strategies for survival as old ones fail. We have seen this throughout Earth's history. Mass extinctions periodically devastate biodiversity, yet life recovers, diversifies, fills empty niches. The Permian extinction 252 million years ago killed perhaps 90% of species, but within a few million years life had rebounded. Dinosaurs dominated for 165 million years, then vanished in the Cretaceous extinction, but mammals rose to take their place. This resilience suggests that even as conditions deteriorate over the next billion years, life might not simply fade away but continually adapt to the slowly shifting baseline. However, there are limits to adaptation. Evolution works with the variation present in populations, selecting traits that enhance survival and reproduction. But it cannot create fundamentally new biochemistries on demand. If atmospheric CO2 drops below levels required for any photosynthetic pathway, evolution cannot invent a new form of photosynthesis that works without CO2. Not because of any failure of evolutionary mechanisms, but because photosynthesis by definition requires fixing carbon from atmospheric CO2. Similarly, if temperatures exceed the thermal tolerance of proteins and enzymes, no amount of selection can maintain active metabolism beyond that threshold. The chemical bonds simply break down. Life operates within physical and chemical constraints. Evolution is powerful but not omnipotent. As Earth approaches the boundaries of habitability, organisms will increasingly find themselves in conditions where no adaptation is possible. The question is when those boundaries are crossed. Is it in 500 million years? 800 million? 1 billion? The answer depends on variables we cannot precisely measure: the exact rate of solar brightening, the efficiency of silicate weathering, the feedback between climate and biology, the configuration of continents. Some scientists propose that complex life, animals, might disappear well before all life. Animals have higher energy requirements than microorganisms, require oxygen for respiration, and depend on ecosystems with sufficient productivity to support food webs. As these conditions deteriorate, animals would face existential pressure. Insects might persist longer than vertebrates due to their smaller size and lower metabolic demands. Some invertebrates could endure extreme conditions. Tardigrades, for example, can survive desiccation, extreme temperatures, and even the vacuum of space in dormant states. Microorganisms are the most resilient, capable of exploiting minimal resources, tolerating extreme conditions, and entering dormancy for extended periods. If Earth 1 billion years from now retains any surface life, it is likely microbial, bacteria, and archaea eking out existence in marginal environments. Perhaps in hypersaline pools where water remains liquid despite high temperatures. Perhaps in subsurface aquifers insulated from surface extremes. Perhaps in endolithic communities, microorganisms living inside porous rocks where enough moisture and protection from radiation exist. These would be the last holdouts, the final representatives of Earth's biosphere before conditions become utterly uninhabitable. Yet even in this diminished state, the Earth would be remarkable. A planet still orbiting its star, continents still drifting, oceans still present even if warmer and less biologically rich. Geological processes continuing, volcanoes erupting, sediments accumulating, crystals growing in cooling magma chambers deep underground, atmospheric processes generating weather, winds, storms, perhaps rain in some regions, clouds forming and dissipating, the electromagnetic dance of the magnetosphere interacting with solar wind, moonlight, dimmer due to the moon's increased distance, reflecting off whatever surfaces remain, auroras shimmering near the poles as charged particles interact with the atmosphere. Earth would still be a dynamic system, a planet in the fullest sense, even if no longer a living world as we understand life. And it would not be unique. Other planets in the galaxy are undergoing similar transitions, their stars aging, their conditions evolving beyond the narrow window where life can flourish. Earth's fate, while poignant from our perspective, is part of a universal pattern. Let us consider briefly the view from space. An observer in orbit 1 billion years from now would see a planet changed. The color of the continents altered, less green, more brown and tan, reflecting the loss of vegetation. Polar ice caps possibly absent or greatly reduced if temperatures have risen sufficiently. Cloud patterns different, reflecting altered atmospheric circulation and water distribution. The oceans might appear slightly different in hue depending on temperature, salinity, and suspended sediment. The day-night terminator, the boundary between illuminated and dark hemispheres, would sweep across unfamiliar continental outlines. City lights, which currently mark human presence, would be absent. Either humanity is gone or has transcended the need for such primitive illumination. The astronaut might feel a profound loneliness observing this world, so similar to home in its planetary mechanics, yet so different in its details. A planet without voices, without witnesses, where the only sounds are wind, waves, and the slow grinding of geological processes. Beautiful in its desolation, haunting in its silence. We should acknowledge uncertainty. Much of what has been described is extrapolation from current scientific understanding, but that understanding is incomplete. Climate models have uncertainties. Geological predictions involve assumptions about mantle dynamics we cannot directly observe. Biological projections assume evolution proceeds without intervention or catastrophe. There are known unknowns, factors we know matter but cannot quantify precisely. And there are unknown unknowns, factors we have not identified or understood. It is possible that processes we have overlooked will substantially alter Earth's trajectory. Perhaps some negative feedback mechanism we do not yet recognize will stabilize the climate beyond what models predict. Perhaps plate tectonics will cease earlier or continue longer than expected, fundamentally changing geological evolution. Perhaps life will prove more resilient or more fragile than anticipated. Perhaps stellar evolution proceeds slightly differently than models suggest. Science advances through refining predictions against observations, but observations 1 billion years hence are impossible. We work with the best tools available, accepting that uncertainty is intrinsic to deep time prediction. This uncertainty should not paralyze us into agnosticism. While we cannot predict every detail, broad trends are clear. The sun will brighten. This follows from well-understood stellar physics. Silicate weathering will draw down CO2. This is observed operating today and will continue. Continents will drift. Plate tectonics is an established fact. These processes, and their consequences, give us confidence in the general picture even as specifics remain uncertain. It is rather like predicting that winter will come, snow will fall, and temperatures will drop without being able to say exactly which day the first snowflake will land or precisely how much snow will accumulate. The overall trend is clear even if the details are not. For Earth 1 billion years from now, the overall trend is toward a hotter, drier planet with a stressed biosphere. The exact state at that moment, whether life persists, where continents sit, whether oceans remain, involves more uncertainty, but the direction is clear. This distinction between high-confidence trends and lower-confidence details is important for honest communication about deep-time predictions. There is a philosophical dimension to contemplating Earth's distant future. It confronts us with our own impermanence, not just as individuals but as a species and even as a biosphere. The Earth does not exist for us. It existed for billions of years before us and will exist for billions after. Our tenure is a brief flicker in geological time. This realization can provoke different reactions. Some find it nihilistic. If everything we build, everything we care about is ultimately erased, what is the point? But another perspective sees liberation in this impermanence. It frees us from the burden of needing everything to last forever. We can find meaning in the present, in the experiences and connections we have now, without requiring them to echo through eternity. The Earth's future is not about us. It is simply the continuation of planetary processes that predate our existence and will outlive us. There is a kind of peace in accepting this, in recognizing that we are part of a larger pattern, temporary expressions of matter and energy organized briefly into the phenomenon we call life. Moreover, contemplating deep time cultivates humility. Our day-to-day concerns, even our civilization's long-term projects, operate on timescales of years to centuries at most. Geological time dwarfs these spans utterly. Recognizing this can recalibrate our sense of importance and urgency. Problems that seem intractable on human timescales may be ephemeral fluctuations on geological scales. Conversely, changes we make now, altering the atmosphere's composition, driving species extinct, reshaping landscapes, have effects that persist far beyond our lifetimes. Our actions ripple forward through time in ways we cannot fully predict. This should inspire both responsibility and humility. Responsibility because we affect the future, humility because we cannot control it. The Earth will continue on its trajectory regardless of what we do. We can alter details, perhaps slightly shift timelines, but the broad arc of planetary evolution is beyond our influence. This is neither defeatist nor nihilistic. It is simply recognizing the scale of processes larger than ourselves. Let us return to the planetary mechanics for a moment. Throughout this journey 1 billion years into the future, we have focused on Earth. But Earth does not exist in isolation. It is part of a solar system, which is part of a galaxy, which is part of a universe. The solar system itself evolves. The sun brightens as discussed. The orbits of planets shift slightly due to gravitational interactions, though over 1 billion years these shifts are minor. Jupiter, Saturn, and the other giant planets continue influencing the inner solar system through their gravity, occasionally deflecting asteroids or comets toward or away from Earth. The asteroid belt, that debris field between Mars and Jupiter, slowly grinds its components down through collisions. Comets from the Kuiper belt and Oort cloud occasionally plunge sunward, some potentially impacting planets. The solar wind continues streaming outward, shaping the heliosphere, the bubble within which the sun's influence dominates over interstellar space. The galaxy itself rotates, the solar system completing an orbit around the galactic center roughly every 225 million years. Over 1 billion years, about 4 to 5 galactic years. 1 billion years is a strange duration. Long enough that everything familiar transforms. Short enough that the basic structures, star, planet, moon, remain. It is a human impulse to seek narrative in such spans, to imagine a story with beginning, middle, end. But geological time does not provide satisfying narrative arcs. There is no climax, no resolution, only continuous change without authorial intent. The Earth 1 billion years from now is not a conclusion but a snapshot of an ongoing process. Earth will continue evolving beyond that point, toward even more extreme conditions as the sun continues brightening. In perhaps another billion years beyond that, 2 billion years from now, conditions will likely have become completely uninhabitable for any life. The oceans may have evaporated entirely, the atmosphere stripped, the surface molten in places. Eventually, in about 5 to 7 billion years, the sun will exhaust its core hydrogen, expand into a red giant, and engulf the inner planets, possibly including Earth. That is the ultimate fate. But 1 billion years from now is not that endpoint. It is merely a waypoint on a much longer journey. What can we take from this meditation on deep time? Perhaps a sense of perspective. The problems we face today, while urgent and important, are not the final word on Earth's story. Life has persisted through multiple mass extinctions, through dramatic climate changes, through the rearrangement of continents and the rise and fall of oceans. It has proven remarkably resilient. But resilience is not invincibility. There are limits. The Earth of 1 billion years hence likely approaches or exceeds those limits for complex life. Yet even in decline, even approaching the end of habitability, Earth remains a world of processes and phenomena, a planet obeying physical laws, a stage on which the drama of matter and energy plays out. There is beauty in that, a kind of austere grandeur. The universe does not care whether we find it beautiful, but we can choose to see it that way. We can choose to appreciate the immense scales of time and space within which our brief existence unfolds. We can feel awe at the fact that the matter in our bodies was forged in stars, cycled through planets, and will continue cycling long after we are gone. As we approach the end of this journey through time, let us appreciate where we are now. Earth today, in this present moment, is a paradise by comparison to what it will become. We have liquid water in abundance, an atmosphere rich in oxygen, a climate that, while changing, still supports vast biodiversity, continents in configurations that create diverse environments, deserts and rainforests, tundra and savannas, mountains and plains, oceans teeming with life, a biosphere interconnected and complex, the result of nearly 4 billion years of evolution. This is an extraordinary moment in Earth's history, not special in the sense of being designed for us, but special in the sense of being within the narrow window where complex life flourishes. The Earth has been habitable for billions of years and will remain so for hundreds of millions more. But even those vast spans are finite bookends on an even longer timeline. We exist in the middle of Earth's habitability, poised between its sterile youth and its sterile old age. That is worth recognizing and, perhaps, worth preserving for as long as we can. One final thought before we close. Contemplating Earth's future can feel melancholic, even grim. But consider this: billions of years from now, long after Earth has become uninhabitable, long after our sun has died, the matter that comprises this planet will still exist. The atoms will be dispersed, perhaps, ejected into space when the sun sheds its outer layers, or locked in the white dwarf remnant of the sun's core. Some of those atoms will eventually be incorporated into new star systems, new planets, perhaps new life. The carbon in your body, the iron in your blood, the oxygen you breathe, these atoms are billions of years old already, cycled through multiple generations of stars. They will continue existing and cycling for billions or trillions of years more. In a sense, we are part of an eternal material continuity, even though individual forms, planets, organisms, civilizations are temporary. This is not immortality, but it is continuity of a kind. The universe remembers nothing, but it preserves everything in altered form. That is the nature of existence at the deepest level, and perhaps that is enough. And so we return to the present, having journeyed 1 billion years into Earth's future and back. We have seen a planet transformed by the slow burn of stellar evolution and the patient reshaping of geology. We have witnessed the stressing and possible collapse of the biosphere under conditions beyond life's capacity to adapt. We have contemplated continents in new configurations, oceans altered, atmospheres changed. We have acknowledged uncertainty and limitations in our predictions while recognizing the broad trends we can discern. This vision of the future is not prophecy but extrapolation, not certainty but educated projection. It rests on our best current understanding of planetary science, tempered with humility about what we do not know. If contemplating such vast timescales leaves you feeling small, remember that smallness is not the same as insignificance. You are part of this story, a brief arrangement of atoms that can nonetheless think, feel, and wonder about its place in time. The Earth will change. Life will struggle and perhaps fade. The sun will brighten and eventually die. But in this moment now, we are here. We can appreciate the extraordinary fact of existence, the privilege of consciousness, the beauty of a living world. That is the gift of the present, and no vision of the future can diminish it. Sleep well, and carry that perspective gently into your dreams.